So have you ever really thought about what it takes to get a machine learning model from just an idea, a sketch on a whiteboard, into a tool that's actually working out there in the real world? It's this whole journey, right? And it's packed with big decisions, really clever tools, and yeah, a few hidden traps you got to watch out for. Okay, let's just jump right in and break down the entire machine learning lifecycle from start to finish.
You gotta love this way of thinking about it. Picture a data scientist as a master chef. They can spend weeks, even months, in the kitchen perfecting a new recipe. That's the model. But what good is the world's best recipe if it just sits in a book on the shelf? The real point, the whole reason for its existence, is to be served to people, right? It only matters when it's out there, deployed, and actually making a difference. Before we get into any of the fancy algorithms or complex stuff, every single supervised learning project comes down to this one question. Seriously, it's the first and most critical fork in the road, and the answer you give here pretty much decides the entire path you're about to go down.
So what are these two paths? Well, on one hand, you've got regression. This is all about predicting a number, some continuous value. Things like, what's the price of this house going to be? Or how many sales will we make next quarter? Then, on the other hand, you have classification. This is totally different. Here, you're trying to pin a specific label on something. Is this email spam or not spam? Is this transaction fraudulent? Yes or no?
And this is the perfect way to see the difference with your own eyes. Look at the left, the regression problem. The model's job is to draw the best possible line through all those dots to find the underlying trend. Now look at the right, the classification problem. The model isn't trying to go through the dots at all. It's trying to draw a line between them, to build a wall that separates one group from the other. Two totally different goals.
All right, so once we know what kind of problem we're up against, it's time to actually start building. This is where we get to open up the toolbox and pick our learner. That's just the fancy name for the algorithm that's going to chew on our data and find the patterns. And believe me, that toolbox is packed.
For instance, you could grab a neural network. These are kind of modeled after the human brain, and they're amazing for finding really complex, twisty patterns in data. Or you could go with something simpler, like a decision tree, which basically just learns a bunch of if this, then that rules. And here's the key thing. There's no single best tool. It always depends on the specific job you're trying to do.
And the options just keep on coming. You've got things like support vector machines, which are absolute wizards at finding those boundary lines we just saw for classification. And then you have these powerhouse models like XGBoost, which are super clever. They actually take a bunch of simple, weaker models and combine them into one incredibly accurate supermodel.
Okay, so you've picked an algorithm, you've fed it data, and now it's spitting out predictions. Awesome. But that leads to the next huge question, maybe the most important one. How do you know if it's actually any good? I mean, are the predictions it's making useful or just noise?
Well, just like we had two different types of problems, we have two different sets of rulers to measure success. It makes sense, right? You wouldn't use a measuring tape to check the temperature. For regression, we use metrics that tell us how far off our number predictions are on average. For classification, we're using metrics like accuracy or precision to see how often we're pinning the right label on things.
Now, check this out. This is a really cool visual for grading a classification model. It's called a ROC curve. Let's say you built that spam filter. You want it to catch as much spam as possible, right? But you definitely don't want it to accidentally throw your boss's important email into the spam folder. This curve shows you that exact trade-off. The more this line pushes up and to the left, the better your model is. It's like a report card, you can see at a glance.
Okay, so we've walked through the perfect textbook version of the process. But let's be real, the real world is messy. There are a few classic mistakes that trip up almost everyone when they're starting out. So let's talk about how to sidestep them.
If you remember one thing from all of this, let it be this. It is so easy to get excited about trying the latest, greatest, fanciest algorithm. But anyone who's been doing this for a while will tell you, your model is only as good as the data you feed it. The real magic, the real hard work, happens in cleaning and preparing your data. Garbage in, garbage out. It's as simple as that. And here is a super sneaky trap that can ruin a whole project: data leakage. This is what happens when some information from your test data, the data you're saving for the final exam, accidentally contaminates your training data. It's like letting your model get a sneak peek at the answer key. It makes you think your model is a genius, but in reality, it just cheated.
So, we've built a solid model. We've steered clear of the big traps. Now it's time to get this recipe out of our test kitchen and into a real restaurant. We need a way to serve our creation to potentially thousands or even millions of people reliably, and that right there is deployment.
So how does that actually work? Well, it usually boils down to these 4 big steps. First, you got to package the model up into a single file. Second, you build an API, which is like a digital waiter that takes orders and delivers predictions. Third, you stick it all on a server so it's running 24/7. And finally, and this is crucial, you have to watch it, monitor it, and make sure it doesn't start going off the rails over time.
Let's just double-click on that first step for a second. Serialization. This is basically the process of taking your model, with all the smarts it learned during training, and saving it as a single portable file. Tools like Pickle do this by essentially taking a snapshot of the model, freezing it in time so you can easily move it anywhere you need it to go.
But, and this is a really big but, here's where things can get a little scary. Most of the time, we don't train huge models from scratch. We download them from public places online. It's super convenient, but that convenience opens up a massive security hole. What if that file you just downloaded has a malicious surprise hidden inside?
And that brings us to this idea of a malicious AI model. And let's be clear, we're not talking about a bug or an accident. This is a weapon. It's a model file that someone has deliberately tampered with to include harmful code, and it's just sitting there, waiting for someone to load it.
So how does the attack work? It all comes back to that serialization step. A format like Pickle, the one we just mentioned, is so flexible that it can actually run code when you load the file. An attacker can craft a model file that looks normal, but the second you load it, bam, it executes their malicious code on your system. And that's the truly terrifying part. The damage is done before you ever even ask the model for a single prediction.
This is why the file format you choose is absolutely critical. Risky formats like Pickle basically mix the model's data and potentially executable code all in one bucket. But newer formats like safe tensors were built from the ground up to prevent this. They build a solid wall between the model's data and any code, effectively slamming the door on this type of attack.
Okay, I know that was a lot to take in, from basic concepts all the way to cybersecurity threats. So let's tie this all together with a perfect example, something you probably see and interact with dozens of times a day without even thinking about it.
What do you think this number is? 8 to 10%. This is what YouTube considers a great click-through rate. It means if 100 people see a thumbnail, an excellent video will get 8 to 10 of them to actually click. For anyone making content, hitting this number is the absolute holy grail.
And how do they hit that magic number? You guessed it, machine learning. The YouTube system is a gigantic, constantly running model. It's testing everything, different thumbnail images, different titles, different colors, on millions of users to solve one big problem. Which combination is most likely to make you click? It's a deployed model that's fine-tuned to create that perfect little curiosity gap that you just can't resist. And really, it brings our whole journey full circle. You have the problem definition, predicting a click. You have the models being built and constantly evaluated. And you have deployment at a truly massive scale, all designed to influence our behavior. So it leaves you with a final thought. The next time you're scrolling and that one thumbnail just seems to jump out at you, was that really your choice? Or was it just the perfect prediction?